get started now. So welcome to the first High Energy Physics GSPS of the semester. Today we're going to have our very own Alex Roman. So as many of you know, he works with Professor Machev and Macheva, and this project was on finding symmetries in their algebras using machine learning. So you're going to see some really cool animations on this talk as well.
You know, Roy is being modest here. He's actually a co-author on all these papers I'm going to be showing. So, okay, thanks everyone for coming. I'm excited to show you what we've been working on for these last few months. Okay, let's get started. So I'm going to motivate it, give a little background on group theory, Lie groups, looking around, I don't know, you might all be super familiar with this stuff, so we might skip over that. And then we're going to talk about our methodology for actually finding known Lie groups, and then get on to some new Lie groups that are in data. Okay, so there's been a lot of interest recently in finding symmetry in machine learning models and in data sets. This is sort of part of a broader movement to make machine learning more rigorous and less ad hoc, and it sort of dovetails with this idea of geometric deep learning. There's like an Erlangen program where we should figure out the symmetry groups of deep learning models and figure out what works and why. So this is sort of in the vein of that. A little refresher on what Lie groups are. So a Lie group is a continuous group. It's a group that's also a manifold. And you can parameterize it given some generators like this. So every element of the Lie group is given as a matrix exponential, or the exponential of the operator, which is some linear combination of these generators. So you have some set of generators G. We're going to be using those throughout. And it satisfies some nice axioms that need to happen. And of course, you all know that these are very important in physics. A little concrete thing to keep in mind is the group of symmetries in 3 dimensions. So there are these generators of symmetries, and these things, the first thing to be unconfused about is that these are not themselves the transformations. If you act these on a vector space, it will not be a symmetry. These are the generators of symmetries. And what that means is that if I put them in exponential, and the matrix exponential is some parameter optionally, I get a transformation. And here's where I was thinking it would be nice. I love going over basic stuff. So the matrix exponential, we define it like this, but for matrices, it actually converges if you have some nice properties. So in this case, if we just want to exponentiate this matrix, you notice first of all that if you square the matrix, you get this sort of negative identity matrix in 2 components.
Could we maybe turn those lights off? It's a little hard to see the blue,
sure,
at least on this screen.
Let's see if we can do that.
Sorry about that. Yeah, that's better.
Okay. Yeah, these projectors are not the best. Okay. So if you have an odd power or an even power of this matrix, you just get the identity matrix, at least in these 2 components. And if you have an odd power, you get that times the thing you started with. So the whole thing splits into 2 sums, which you can recognize as cosine and sine, and you end up, this is how you go from here to your familiar matrix, your familiar transformation matrix. Oh, actually, this is a mistake. There should be a 1 here, because in the 0 term, you have the 1. Okay. So a Lie algebra is the algebra of the generators. So this is a little different from the group, which is these elements we were just looking at. The algebra is the linear, the span of all these generators, linear combinations of the generators. And it's equipped with a special thing, the Lie bracket, which we're used to seeing it as the commutator. And this, you can think of it as describing the infinitesimal transformations of the group. So you're familiar with these. And the important thing I want to point out here is that they have to satisfy, some sort of closure condition. So if I take any combination of these 2 generators and put them in the Lie bracket, I end up with something else which is in the Lie group. In this case, in the case of the polymatrices, it's exactly one of the generators, but for closure, you only have to get it that it's in the span. So there's some linear combination of these generators which gets you each commutator. So we're going to be using this in a second. Okay, so our idea here, that's the background. Our idea is to parameterize these things and actually learn them from data. And what we mean, okay, so first of all, the generator we saw is like this, which means the first order in the parameter here, if it's a small parameter, the transformation you get from this infinitesimal generator is just 1 plus epsilon times that generator. We have some code here, and this is exactly how it's written. There's some apparatus to make it work, but essentially what's happening is whatever you input, you get that, the identity acting on that, plus epsilon times the generator acting on that. So the generator is some sort of, well, it's in fact a PyTorch model, and we get to choose that. We can make it any arbitrary neural network model that we want. That's how we chose to do it. In the cases that we're going to see now, until I say otherwise, we are just taking that neural net to be the simplest possible neural net, which is one with no hidden layers and no bias and no activation function. Okay, parse that for a second. That just means a matrix. So it's just a linear transformation. But we keep it general, so it's easy later to change it and make it more complicated when we need to. Okay, so we parameterize these generators, and we learn something, but the point is we want to learn symmetries. And that means symmetries of something. So we call this an oracle. This is something which acts on your sample, and you want this thing to be preserved by the generator that you find, by the symmetries that you find. So if I'm in d dimensions, it's perhaps just some scalar function of my samples. So let's take an example. Let's say, okay, so first of all, what do we really want? We want to design a loss function which preserves these conditions. So what are the conditions we want exactly? Well, we want it to preserve the oracle, so we want this thing to be equal to that, so we just introduce a term. We say, okay, a term in our loss function is how much the oracle gets changed when I operate my infinitesimal generator on it. Now you notice then some details like that this thing scales as epsilon on the inside, so we normalize it like that. Okay, so are we done? Is this the whole thing? So this is very nice. This will indeed give you some function which preserves the oracle, but there's a problem. So you want to see what the problem could be? If you try to train this thing, try to learn a generator which makes this true, what generator do you think you'll find? Did you say the zero map? Yeah, something which just, trivial, it's a trivial generator. It's not a generator of anything, it's just a zero map. So this would be trivially satisfied if this thing didn't exist. Okay, so we got to normalize it to avoid this problem. So let's include a condition which somehow makes it so the transformation is not trivial. There are two ways we could do this. First, we could look, we know that transformation is just a matrix for now, so we could just look at the parameters of that matrix, meaning the entries, and we could constrain those. Or we could look at the action it has on the data set. And I need to explain in a second what is the data set. So these both have some advantages and drawbacks. The advantage of this one is it's well-defined. It's clear what this would mean to put some constraint on these things. This is actually how it works in mathematics. There is already a notion of a metric on how to normalize matrices. However, this doesn't seem, it's not clear how to generalize to this. So that's the advantage of this, is that it would actually work with a more complicated matrix. So for now, we're going to go with option A. And so we're just going to normalize and say, like, oh, the sum of the squares of the parameters need to be 2, or some constant, doesn't matter what. We choose 2 so that it corresponds to the things we usually expect to see, but that's not actually important. Okay, so essentially, this is like if you flattened out the matrix and just looked at it as a vector, use dot flatten. This is constraining the length of that vector. So the results are, when you put these two things together, so this is our loss function so far. We have an invariance term, which averages over some points. So we draw some points that we're interested in finding the symmetry of the the oracle on those points. And then we have to average our thing, which depends on those points, our invariance loss term across the entire data set. So we have something on which to act. And then we have this other thing which keeps the action normalized, so it's not trivial. Okay, so again, we parameterize this matrix, which is just all the generator is for now. That's just 4 variables. And I'm going to visualize the matrix with this kind of image, which is just a sort of show of this. The white corresponds to a 0 in the matrix, and you see there's a little color bar here. The red is net -1, and this one is +1. Okay. So what happens when we actually train on this loss function? Well, you can see what's going to happen. So let's see what happens to the matrix. So it actually just magically morphs into exactly the generator would want. So we go from some untrained thing, and it basically makes it anti-symmetric. And that turns out to be up to minus sign the unique solution. So what does this thing correspond to? So this, if I act this on every point in my data set, in my space, this corresponds to like a vector field, a flow. It maps from vectors to vectors, of course. These things are always square matrices. Or when we proceed from matrices to more complicated transformations, they'll always map from d dimensions back to d dimensions. So it makes a flow on this vector space. Every point gets sent somewhere. However, it's also the constraint, our invariance constraint is essentially saying that these vectors need to follow the contours of our oracle. So if we evaluate our oracle everywhere, our oracle, remember, was just the length, so it just makes a sort of distance map. And so these vectors are learned in such a way that they follow along the contours of the oracle. Okay, so far, now we can learn multiple of these in parallel, because remember, what we're getting at is finding a group of these things. So far we've learned one. We can learn multiple of them in parallel that are sort of uncorrelated, and we can train them. And here I'm showing the same matrices again, and we can watch them train. And they anti-symmetrize themselves. But they end up as, and here I've drawn the axes of rotation. And in this case, since they're uncorrelated, you get some sort of random axes. It essentially picks them randomly from the sphere. And so this is fine, but we realized that we can introduce another term, which is sort of well motivated from looking at the math that this comes from. Essentially, the normalization term we introduce is like the norm according to some metric on matrices, which is the trace of the thing with the transpose of another thing, or the flattened dot product kind of thing. So we can use the same notion of a metric to define what it means to be orthogonal, for these matrices to be orthogonal. And so we go with this option again, and you see that we essentially sum over different pairs of these things. So we go bump, bump, bump. And the thing inside is this dot product. Or you can also write this a trace if we want to keep it in matrix notation. So far, I want to write down a recipe. So the recipe for making this is that we have to include invariance. We've seen that we need normalization. Sorry, it's going a little behind there for you guys. And we haven't quite seen that we need orthogonality, but it seems nice. And we'll see a use of it later. Is there anything else we need? Is there any other ingredients that would make this recipe better? So one thing you might notice is that these matrices are sort of, okay, so first of all, I gotta show you what happens when we turn on the orthogonality term. So when we turn on orthogonality, now instead of picking just random vectors, they're now correlated. And as you train, it eventually converges to something which is an orthonormal basis, which is pretty cool. So you can see here the angles are printed. I have a better version where they actually go to 90. This is actually the data-driven one. But, okay, so now we're finding some nicer thing, but there's still sort of these random bases. Okay, I mean, they're now orthogonal, but they form a sort of random basis. And here I have the basis for so we've seen SO2, that was the first example. This is SO3, rotations in 3 dimensions. We've also learned SO10, which is rotations in 10 dimensions. But they're all sort of just like random, in some random basis. So now we have this idea that we can include a term which encourages sparsity, because any basis will do. And if you think about it, in say 3 dimensions, there's sort of a, I suppose it's like a 2-sphere of these different bases I could choose from. Maybe it's a little more complicated than 2-sphere across a 1-sphere or something. This is essentially breaking the degeneracy on that surface, because our loss function is the same for every basis. The sparsity term says, oh, actually, can you find a basis where the representation is sparse? And so we have a paper on this, or one of our other papers deals with this. And you can see what happens when you turn on the sparsity term. So without the sparsity term, you get these random bases. With a little bit of the sparsity term, it's helping a little. And then with the right range of sparsity, you end up with these really nice bases which are much easier to read off. These nice matrices which do some sort of clean rotation. You know, here it's a rotation between the 2 and the 3 component. This is in 4 dimensions. But there is a problem, which is that if you have too much sparsity, it starts to overwhelm the thing. So the right answer, you know, we kind of know what the right answer is. We know the right answer is not totally sparse. So in this case, it's a little complicated. So in this case, this is the right answer, but this is sparser. And so if you have too much sparsity, you will actually find this instead of the right answer. So it's actually kind of irreconcilable with this one. So a little bit helps, but too much breaks it. So okay, so just we need to add a dash of sparsity to our recipe. And so you can actually see the effect that the sparsity thing has. So before we were learning sort of rotations around random axes, now they're decoupling in nice ways. So for SO3, the axes look like this, and you get the nice rotations you're used to. In 4 dimensions, it's a little trickier. The color here indicates the coordinate in the 4th dimension, white being when it's 0. So you can actually see that it decouples into regular rotations and rotations between one of the axes in the 4th dimension, which looks like that apparently. It's very pretty. So sparsity seems like a very nice property if you want to make these things actually understandable. Okay, so one more thing. We talked earlier about closure of these groups. So now we can add another term to our loss function. And this term will ensure that any vectors you have are in the span, or pardon me, the Lie bracket of any 2 of your generators you've learned has to be a linear combination of the other generators that you've learned. So this is like, we formalize this by saying the Lie bracket minus the sort of projection operator acting on the Lie bracket, where the projection operator projects into the span of all the generators that you have. This thing ought to be 0. Like, it ought to be in this subspace, the span of those things. So if it's outside of there, this vector is not 0. So we can add this little ingredient to our loss function. And now we can see some really interesting structure starting to emerge. So what I'm showing here is for 2, 3, and 4 dimensions, we're going to train multiple times, but we're going to choose different numbers of generators, okay? So the number of generators is something you specify at the beginning, kind of like if you're familiar with like k-means clustering, this is like a hyperparameter that you choose. So we saw that in 2 dimensions, we can learn 1 generator, okay? What happens if we try to learn it again with 2 generators? Well, we should look at our recipe and ask, is anything going to be a problem? Is our loss function going to be unsatisfiable in some way? And the answer is yes, but where? So you can certainly find two matrices which are both invariant transformations of length in 2 dimensions, but will they be different? So the orthogonality term becomes a problem. There's actually only one answer, which is the 1 minus 1, and then there's the minus that minus 1 1 on the off diagonal. So there's not two orthogonal generators of the symmetry. So actually it's impossible. I told you we would eventually see the use of orthogonality. It's able to help us find out the maximum number of generators you could have for a certain symmetry. So, so here, where we try to train with 2 generators, you can see the loss function never goes down. It's impossible to learn this thing the way we set it up. Okay, so that's interesting. So again, in 3 dimensions, we can train with 3 generators. This is what we saw before, right? We know that works. Clearly, you can have 3 generators of rotations in 3 dimensions, x, y, z axis, for example. Perfect. Now, if you try to train with 4, can you think of a 4th, axis, which is not some linear combination of the other axes? No, that's actually impossible. And you can see that because this red line where we train it with 4 generators never goes down. There's 2 more lines on this plot. So if you train with just 1 generator, okay, you can pick 1 generator. It's invariant. You can make it normalized. It's trivially orthogonal because there's nothing for it to be orthogonal to. So that term doesn't contribute anything. You can make it sparse, and it's trivially closed. There is no Lie brackets to calculate. So that is sort of trivial. The interesting case comes here. When you have n equals 2, there's actually no way to do this, but why? It's not orthogonality that's causing the problem. Now the problem is that you can't close 2 rotations. If I rotate with x and rotate with y only, the commutator of that is a z rotation, turns out. And that's not one of my generators, so it's not a closed group. So this thing is actually now the advantage of including all these terms in a recipe, and you finally see why we bake the cake this way, is that we can do some cool stuff with it. Orthogonality limits how big the group can be. Closure tells you whether or not there's substructure with that many generators. Okay, and so now we get to the really interesting part. Let's try 4 dimensions. Okay, in 4 dimensions, you might happen to know SO4 has 6 generators. This comes from 4 choose 2. You can choose 2 axes and rotate with respect to those. So there's 6 ways to choose 2 axes in 4 dimensions. So let's try everything. We know 1's going to work. I didn't even draw that. Let's try all these numbers. And I have this drawn here in a plot where I have the number of dimensions we're in and the number of generators. And then the color denotes whether or not I was able to find it. It actually denotes the final value of the loss function. So here in the blue, we got some low value of the loss function stop training. In the red, we were never able to converge. These are the lines that never went down. So you can see what we've talked about so far. 1 generator for 2 dimensions works. Any more can't be orthogonal. For 3 dimensions, 1 works, 3 works. 2 is not closed. Any more can't be orthogonal. In 4 dimensions, we know 6 works. That's not that surprising. Some interesting features. 1 works, that's trivial. That's always going to be the case. 3 works. This is actually an interesting feature, which is corresponding to the fact that SO3 is a sub-algebra of SO4. So if you just take 3 generators, force them to be closed in SO4, you will get SO3 out of that. Now there's 2 more dots that need, or cases that need explaining. This one puzzled us for just a second. We said, wait, 2? How do you have 2 things that commute? If they commute, if you put the commutator of those 2 things, won't that be something other than those 2 things? There's another option. It could be 0. They could have 0 commutator, and then it would be closed. So this is actually an abelian subgroup, which turns out to be the case. That exists. And then this one really surprised us. We did not expect, here's the generator of it, we did not expect this to happen. It turns out this is a known thing. This is isomorphic to the group of similitudes or something. So this is some sort of unknown fact by us. Unfortunately, it was known by the rest of science. So that would have been very exciting for constant linear. But that sort of shows the power of this approach, is that we were able to actually learn something about pure math that we didn't know, we didn't put in. We got more out than we put in, which is sort of what you hope to see. We will go all the way up to SO5. There's no more structure there. SO4 is a subgroup of SO5, so all the subgroups of SO4 get inherited by SO5. So that's all I have to say on that topic. But it's very cool that we were able to, find this. Okay, so we can go one step further, and you can train, for instance, 6 generators and insist on a certain kind of factorization structure. So we were previously saying, let's learn only the first 3 and force them to be closed. But now, as another step, this is sort of the most recent work we've done, is it's never before seen in my group, except for in the email I sent. So these guys close among themselves. These guys also close among themselves. And then they're forced to be, so we choose how many we want in each subgroup, in each factor, and we see if it works. And so in the case of SO4, SO4 is actually isomorphic to SO3 cross SO3. And here are some representations which do that. SO4 and the Lorentz group are isomorphic, so you might be familiar from field theory or something about how the Lorentz group, you have the boost in the generators. If you take the sums and the differences of that, both of those form an SO. Well, we usually see this at SO2. So that's a cool feature that you might know from your classes, that this can happen, that you can make 2 SO3s out of SO4. So this is another cool thing. But all right, there's a lot of this stuff. The generators for this, they look really weird because they're mixing up all 4 dimensions. So I thought that looked kind of neat. I don't have a lot of intuition for what's happening here. Okay, so that's pretty much the whole setup. I'll just show you 2 more places where we applied it, and that's pretty much my talk. So we've done SUN. We go all the way up to 10, actually. Now we're going to apply to the unitary groups. And so in the unitary groups, we have to make a couple changes. So previously we were preserving the length of some real vector. Now we're preserving the length of some complex vector. And so the generator, we have to make it more complicated. Now they have complex entries. So we have more entries than before. So to represent one of these matrices, I'm going to draw 2 pictures. I'm going to draw, as before, the real part of the matrix. But now I'm also going to draw the imaginary part. And so now you can see what we find when we try to train this on SU2. So first we train on U2 with 4 generators, and we find this thing. Okay. So that's very nice. I won't go on this much. But if you insist that it's closed, and you say, I would like 3 generators, and ask what it will find, you find this. Does this look like remarkable or familiar to anyone? What are these?
Polymatrices.
These are the polymatrices. So this thing finds the polymatrices. And in fact, this thing differs only by a phase from the polymatrices, because if you add these together, you get the identity. If you subtract them, you get Z3, which is there. So, okay, so we found a basis for U2 and SU2. We can continue to do this. We can try to ask it to do it for U3. We find this, and SU3, we find this. Now, for the people who took the field theory class or relativistic quantum mechanics, does this look familiar?
Gell-Mann matrices.
These are the Gell-Mann matrices, yeah. So a couple of weeks ago, there was a colloquium by Rachel Hoots, and I was talking to her, and she said, oh, it would be very interesting if you guys could apply what you did to SON to SUN and get the Gell-Mann matrices. And so we did. So the most remarkable thing about this whole thing is how easy it was to generalize. Once we wrote the thing for one case, in most of the time you only need to change like one number in the file, run it again, and you get a different case. So this thing just works really well with the exact same recipe. Only some slight modifications to account for the fact it's not complex. Okay, continuing on, we do U4, SU4, and U5, SU5, SU5 and SU6. And the structure just kind of continues the same pattern that we saw in the Gell-Mann matrices. Okay, so that's all I have to say about the sort of like mathematical groups like that we're discovering. now I'd like to switch over to the realm of real data. So we have another paper which is about applying our technique to real data where the generators are more complicated than just a matrix. Okay, because that was the real limitation of what we did before. There we were just assuming that the generator could be represented as a matrix. That's not always true. So I have an example here where I constructed an oracle which was too complicated to be fit by a matrix. So the oracle here is just this like L1 norm of the vector. So it's just the absolute value of the sum of the components. And the level sets look like a diamond, it's very pretty. And so now you ask your thing from before, please find me a symmetry. And it'll say, okay, let me try. And this is what it comes up with. I don't know how well you can see it, but here, there's arrows that are following the contours here and here, but here, the arrows are sort of going across the contours. And that's because you can't make a linear transformation which does something nonlinear like this. It's a problem. So you need to go back and generalize it, make your model more complicated, give it nonlinearity, make it a deep neural network, in order to actually learn this thing. And everywhere we had some choices about how to define these things. We had option A and B, and previously we went with option A, which was just look at the parameters of the matrix. Here, that's not an option because we don't know what the parameters are doing in a deep neural network. That's sort of hard. So here we have to define everything with reference to the action on the data set. And I haven't written out exactly how we do that, but you can kind of imagine that it's something like, oh, look at how the data set gets transformed. What's the length of the, or like what's the rate of flow of that vector field and normalize that or something. Or make it orthogonal as much as you can for two different generators. Okay, so this is able to do that, which is pretty cool. Now there's some issues that come when you try to apply this to an even more complicated domain. So I had this idea that I wanted, from the beginning, I said, I want to apply this to images, or to MNIST digits. But when you're defining that thing I was just talking about, the length, or the rate of flow, or the metric between two different vector fields in this sample space, you need a metric in that sample space. Okay, so in the last picture, I could just use the Euclidean metric. I say, okay, so the length of this vector, I know it. Okay, fine. Now imagine the thing that the space where these vectors are defined, where this vector field is the space of all images. It's not so clear what the metric should be there. So this was the real problem going into this, trying to tackle finding symmetries on images. So our workaround is that we use an autoencoder. So briefly, for anyone who's not familiar, an autoencoder is just a particular architecture for a neural network, and it's defined by the fact that whatever you put in, the output layer is the same as your input layer. That's number one. So it's taking something and returning something of the same size. And the other important fact is that it has to bottleneck down. So you have some compression of the data. So there's two parts to it. It basically takes something and it learns a way to encode it and into some compressed representation, which we call the latent representation, or the points in the latent space. And then it learns a decoder which maps those latent representations back to the original image, or the original type. And then it's trained in an unsupervised way where it's just trying to match the pixels as well as it can. Pixel-wise loss between the original and the retrieved images. Okay, so what this does, this is essentially, if you're familiar with PCA, this is like PCA, but the transformation is allowed to be nonlinear. So you're finding some like compressed representation which keeps most of the important features. So our solution for this problem I was just mentioning about not having a metric was to work in the latent space of an autoencoder. And there we can just use the sort of Euclidean metric. Okay, and so again, to be clear, when I say we want to find symmetries on images, what I mean is we want to preserve the output of some classifier. So if we have a classifier which is trained on it and says this is a 1 with confidence 90%, and it's a 4 with confidence such and such and so on, we want to preserve that output. Now that output is not a scalar anymore. Previously we were only looking at scalar oracles, so we generalize everything to vector oracles. So instead of preserving, make the oracle of the transformed thing the same as the oracle of the original thing. It's actually exactly the same. It's just difference of vectors now. So, okay, so we make these generalizations, and we have this image to sort of show you. Okay, so first of all, I have two things here. This is sort of illustrating the latent space. So this is mapping digits. I did not train this. This is just a very standard thing to do. Mapping digits to 2 dimensions. And then at each point in the 2 dimensions, you can take that point and decode it with this latter part of the latter half of the autoencoder. And you can say, what's the image that corresponds to this one? So they just draw this. So you see that it sort of learns to put like images together and sort of morph them in some nice way between each other. So that's like the solution that it finds to this problem of encoding images in 2 dimensions. So over here, what I'm showing is that we have some feature, these are the images, and we would like to learn some transformation which maps it to a new feature in such a way that the oracle, remember phi is my oracle, which maps it to labels, we want to preserve this thing, okay? So we want the oracle on this, that's this arrow, to be the same as the oracle on this, okay? So we can constrain like that. But like we said, it's difficult to map directly. So our idea is to use an autoencoder and to use the encoder and the decoder, which are written here as E and D. They take us to and from the latent space. And then our idea was to learn a generator on the latent space rather than on the full feature space and go from there. Okay, so I'm showing here the contours of that oracle. It's 3-dimensional in this case. I just did a limited subset to try to illustrate it. So we're going to try to find features which preserve this oracle. And so we do. This is sort of showing another limited example where we kept only the ones and zeros, and we did it in 2 dimensions just to see it. You can keep this thing. You can find a vector field which preserves it. Unfortunately, when we go to 3 and more dimensions, of course, we can't really show it anymore. And we especially can't show the multidimensional oracle. But we are able to learn these things. And so the really interesting thing, so we can't show the vector fields, but we can show the effect that they have on the images. So I've taken some images here, one of each class, and I have taken one of our learned generators, and I am going to sort of walk along that generator and then walk back. I'm going to sort of see how the generator transformed it. And remember, before I play this, the point is to preserve the output of the generator. So you tell me if it does a good job. So these, according to our thing, are symmetries. These are symmetries on the digits, which allow you, which all these different things get classified the exact same way by a classifier. Like this is still mostly a 0. This is still mostly a 5. Okay, so that's kind of the last part of it.
Sorry, I have a quick question.
Yeah.
How many generators did you look for? Only one? Or,
So in this case,
yeah.
the case that I'm showing you now, this case was only one.
Okay.
We have tried a larger number of them, but this is rather hard to train. So we're not very good at doing this yet. So we've tried it with 2 through 6. I don't think I've gone beyond 6. But it still sort of remains to be seen how we can find these rich non-abelian structures in these data sets. But I think the tools are all in place to do that. So I'm really excited about this kind of work. So to just kind of summarize now, this is what we've done. In the mathy, non-data-driven domain, we could try to make things that learn the exceptional groups. In the data-driven domain, we could try to do things that obviate the need for this oracle and look just at the data set themselves in an unsupervised fashion. One other thing is sort of going with what you're asking about, is like, how do you know what is the group structure of this data set? Like, is there a non-abelian structure? So we have not really figured that out yet. That's still an open question. that's what I want to do. And the dream is to be able to really look at this and say, oh, MNIST digits, the Lie group of those is this, and maybe we can actually use that fact to improve the model or to make the model invariant with respect to that or something. And that would just be a really interesting way to sort of try to make this more interpretable. And I've drawn here a dream I had, which would be to look just at the data set and try to find symmetries on that data set without referencing any oracle. So this is sort of where we're going. We've put out 3 papers on this, actually this year, and have them linked here. So, okay, yeah, so that's all I have. Thank you.
Are there any questions?
I've got a really small question.
Yeah.
The autoencoder you used, was that variational autoencoder or was it standard?
No, it's not variational. It's just no, it's just a basic autoencoder. It is convolutional, but it's not variational. All right, I'm happy to chat with anyone if you have other questions or ideas about it. So thank you for listening.